Hi, welcome back. I'm Rakesh Naik. Today we are going to discuss about depth-first search. It is a graph traversal algorithm. But before we start, a small request. If you have not yet subscribed to the channel, kindly subscribe and press the bell icon so that you'll get all the updates from this channel. So, let us start. Till now, we have covered what is a graph, how to represent a graph. Only representation doesn't mean anything if we cannot traverse it. So that's why we are going to discuss about traversal technique, that is depth-first search. A systematic way of visiting each and every node in a graph is called graph searching or graph traversal. Basically, graph traversal is of two types. One is breadth-first search and another is depth-first search. So today we are going to discuss about depth-first search. Before we start about depth-first search, let us try to understand what are the applications, where we are going to apply if we learn depth-first search. Depth-first search is applied to check the connectivity of the graph. It is applied to check whether the graph is acyclic or not, and it is used to find the articulation point. Let us try to learn about the general terms that you are going to use for depth-first search. The first one is depth-first forest. The depth-first forest is a collection of trees in which the traverse starting vertex serves as a root, and as and when we cover the unvisited vertex, we try to add each and every vertex to the root. This is what a depth-first forest is. The next definition is about tree edge. Tree edge is an edge. Whenever a unvisited vertex is reached through an edge, then this edge is associated with the traversal. So this edge we'll say is a tree edge. So every edge in a traversal I'll say is a tree edge. Let us say 5 is not associated with the tree traversal, and let us assume that 5 is an untraversed vertex, and whenever we'll traversing 5, then we'll traverse to 5 through the edge between 7 and 5. Unless we add this edge to this particular graph, we cannot add vertex 5 to this particular graph. So that's why this particular edge, that is edge 7, 5, will be a tree edge. Next one is a back edge. In a graph G, back edge points from a node to one of its ancestor in the DFS tree. So it means what? For this particular vertex 5, there are two parents, 7 and 2. Let us assume that we traverse from 1 to 7 to 5. Then whenever we from 5 we are traversing, we will find one more edge as 2, but it is an ancestor. So such kind of edge we will say as an back edge. Let us try to see what are the steps that we are going to follow. The first step is select an unvisited node V, visited and treat it as a current node. Second one is find the unvisited neighbor of the current node, visit it and mark as a new current node. If the current has no unvisited neighbors, backtrack, go to its parent and mark it new current node. And the fourth step, we are going to repeat second and third step until no more nodes are left unvisited. And in the fifth step, repeat step 1 for the remaining nodes. So we are going to repeat all these steps in order to find the depth-first search tree of a particular given graph. Let us try to do the problem with the help of an example. So let us say this is the graph given. Let us start with vertex 1. We are going to mark it as visit and we want to push it into the step. So before we start, we are having a list of vertices. One is a visited list. So whenever there is all zeros are there, it means no vertex is being visited. If somewhere we'll find 1, it means vertex 1 is visited. So 1 will indicate the vertex is visited and 0 will indicate the vertex is yet to be visited. and we are implementing a stack in order to find the depth first tree. So we are starting with vertex 1. So we'll mark it as visit and push it onto the stack. So something like that we have done. So visited vertex is 1 and in the stack we kept 1. So in the next step what we are going to do, we are pop the stack. It means on the top of the stack 1 is there, so we are going to pop it. But before that we are trying to find the adjacent vertices of 1. So we are having 7, 2 and 4 are the adjacent vertices which are not yet traversed. So that's why we are going to push this into the stack. In a order 7, 2 and 4 we pushed it into the stack. Now on the top of the stack we are having 7. So we are going to pop 7 and find its neighboring vertices. So 7's neighbor is 5 and it is not yet visited. So I want to push 5 into the stack. I have marked 7 as visited and on the top of the stack I have pushed 5 because 5 is neighbor of 7. On the top of the stack 5 is there, we are going to pop 5 and its adjacent vertices, that is vertex 2, we are going to add it. But it is already there in the stack, we need not do anything. Only 5 will be popped out from the stack. So 5 is marked as visited. Now on the top of the stack we are having 2. 2's neighboring elements are 6 and it is not yet visited. So we are going to push 6 into the stack. So in place of 2 we have written 6 and we marked the 2 as visited. On the top of the stack we are having 6 and 6 adjacents are 4 and 3. 4 is already there in the stack, so we need not do anything for 4. So we are going to add 3 to the stack. 6 is popped up and 3 is added. Now on the top of the stack we are having 3. So adjacent to 3 is vertex 8. We are going to push it onto the stack and mark 3 as visited. Now on the top of the stack we are having 8. So we are going to pop 8. No adjacent vertices are there and one more element will be there in the stack. So what we are going to do? We are going to backtrack. So when we'll backtrack, so this I'll say as an back edge. So on the top of the stack now 4 is there. We'll pop the stack and there is no neighboring element yet to be visited. You can see the stack is empty and all the vertices are 1. It means all the vertices are visited. Now we can stop the algorithm. So this is our required depth first search. Now let us try to discuss the depth first search algorithm. So we are taking one array with vertex v, we are marking it as visited, and for each vertex that is adjacent to v, we are taking it and we are marking it as 0 because it is not yet visited, and we are calling again DFS for this particular vertex x which is neighbor to v. So this is a recursive algorithm and this simple algorithm will help you to find the depth first search algorithm. So let us talk about the complexity. So every node is visited once, that's we know, and every edge vx is crossed. It means we are going to visit it. So it means all the vertices and all the edges we are covering. It means the complexity with depth first search is big O of number of vertices plus number of edges. Thank you for watching this video till the end. Keep watching, keep learning, and if you like the video, kindly give a thumbs up, kindly share with your friends. We'll meet again in one more video. Till then, take care. Bye.